think we're live. Can you double check?
Check. Once. Yep, we're live. Yep.
All right. Hello, everyone, and welcome to today's episode. I am your host, Tim.
And I'm Mikey.
This is Sahil. Welcome, everybody, to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. So without further ado, let's get to it. So, Tim, Mikey, this is an interesting continuation of our past episode where we talked about the DESI and the James Webb Telescope in terms of what they're observing in dark matter and how it may challenge the current notions of general relativity and whatnot. And so I think maybe what might be helpful is Mikey, if you could recap the previous episode, and then Tim, if you could set the stage for what we're going to talk about today.
Yeah, so I don't know if it's on my Google News. The last month has just been filled with all of these headlines about like how cosmologists are having to rewrite their story of cosmic history and the universe's expansion and all that stuff. And a lot of this was coming from um, indications from certain experiments that Tim can explain more about. But these indications were um, seeming to suggest that the expansion of the universe um, was not going according to what we might expect from sort of the usual things that we believe to be true about the universe. And to get more into the specifics, what that means is that we have Einstein's theory of gravity, which not only predicts the attraction of planets and why all these things about how gravity affects the structure of the cosmos, but one of the particular predictions of Einstein's theory is that if you have a form of energy that does not dilute as space expands, then this type of energy will cause the universe to expand at an increasingly exponential rate with a constant exponent. So that it makes a very specific prediction about how the behavior of the universe's expansion should look like. And um, so as particle physicists, Tim and I, this makes sense to us, right? Because particle physics predicts that there should be some minimum energy level of empty space, meaning that as you create more empty space, you create more of this energy, just by way of the fact that these two things are inextricably linked. And so this picture of the universe expanding at an exponential rate was it's very comfortable. It makes sense. It's what we mostly observe. But in the last few months, some experiments have claimed to come out, or I guess the scientific media has claimed that these experiments suggest this is not true. That actually the expansion rate of the universe is somehow shifting with time, and that observations of the expansion in early times versus present times don't seem to support this idea of like a exponential expansion with a constant exponent. And if this were true, this would indicate that, maybe some of the most fundamental ideas we have about physics are wrong. And so it generated a lot of excitement and a lot of clickbait. And I think the purpose of today's episode is to maybe take a little bit more of a sobering eye on that whole discussion and maybe walk back some of the excitement. So,
I don't know about sobering eye. I mean, I talked to some of my astrophysics colleague, and I think this is one of the few times that I think there's somewhat of a consensus that this experimental finding it is actually very interesting and it's somewhat exciting because it has been a long time since we find really tangible hints of perhaps new physics. And to reiterate the
in this
point,
particular sector, right? Like, I
right?
mean,
Yeah,
yeah, but as far as the dark energy cosmological constant problem goes, this is the first new thing that's popped up in a long time.
yeah.
So I can,
Yeah, yeah.
oh,
What's up?
I cut him off. I assumed he was going to continue.
Oh yeah, I assumed that too. That's why I wasn't saying anything. were you gonna say anything else, Tim? Or you're
Yeah, I can add a little bit of more information for those who perhaps didn't follow last week's episode. So basically, we're talking about the DESI experiment, which is the Dark Energy Survey Instrument, something like that. I forgot what it stands for, but it's a telescope in Arizona. They map out millions and millions of very distant galaxies, supernova, quasars, and whatnot. And what they measure is how far these objects are and how far they are moving away from us, right? So according to conventional wisdom, if there is a cosmological constant, a positive one, the universe is kind of like putting money in a savings account, right? It's just going to accumulate interest in an exponential rate. It's going to grow exponentially, right? And so far, this sort of has been the conventional wisdom. But what DESI found was there was a hint that this interest rate might actually be getting adjusting. You know, it's not the same interest rate. In fact, the interest rate has gotten lower. I don't know. I guess maybe there's some analog with how our economy is doing right now, but I'm not going to go into that. But basically, it seems like maybe something is setting that interest rate of the cosmos, and if that were true, that would make it super interesting. Because anything that changes, guess what? In particle physics lingo, if something is changing, that means it is a field, a particle physics field, and that means there are particles associated with that field. And if that's true, then that's like a new particle, that's a new force, and that's why you see all over the archive there are new papers popping up left and right talking about this possibility, and we're gonna go into that.
Wait, actually, that's a should we elaborate on that point actually, because that Tim mentioned, because that's like a very non-obvious point that we kind of just glossed over, right? Like if something is changing, that means there must be a field. And that means there must be a particle associated with it, and that's very, very much generally true, right? But how do we convince people this is?
Well, I think it requires a little bit of leap of faith too. Like you have to combine a few facts. Like imagine something is changing, then you say, well, how does it change?
Yeah,
it has to change.
Like minimally, there has to be some parameter that dictates it's changing, and so now you have a field, right? Like if it's changing, and you're saying there isn't any parameter, then I don't know what the hell you're talking about. If it's changing, there has to be something or things, maybe possibly multivariate things that are determining how it's changing. So, okay, boom, we have a field. Okay.
Yeah, I guess you do have to take a small leap of faith, because you have to assume Einstein is right, because
not for what you just said, right? Why do I have to talk about Einstein for what you just said?
Yeah, what I mean is if you have something change, let's say you require that something has to change in time.
Yeah.
Then if Einstein's right, space and time are one and the same, then that thing has to change in space as well. So when something is changing in space, you get waves, so you get particles.
Yeah.
So I guess that's a very small leap of faith. But
even if Einstein is wrong, if something is changing, it still has to be, describable as having a dependent variable, right? That's just
that's true.
And then it's a field.
Okay. Yeah, it might by definition,
it's an evolving field in the traditional sense, but you have to have a field if something is changing.
Wait, hold on, guys. I want to stop, because jargon alert.
Yeah.
What is a field? You guys have said the word field many times.
Literally, what I'm saying is that a field means change, right? Like, so if something is changing, that means a field. Okay, so a field is something that describes a value that depends on something else. So if something is changing, for example, like the temperature of a room, that's like it takes some value, and that value depend on some things like how hot the sun is today, or how sealed the room is. There's some things there's some value that changes over space or time, and that thing depends on some other things. So that's all we're saying here when we say field. So,
but is it as helpful? Because I could even make the argument that if it's constant in all of space and all of time, can't I say that is a field itself as well?
it wouldn't be a very
Like
good
punchy.
field. I mean, like to just say you could might as well you could just as well call that a constant. I mean, so we have these different words, right, to describe things that change dynamically and things that
Yeah.
don't. And things that don't we call constants, and things that do we call fields. So
Yeah.
fields are really just a general description of change.
I guess I'm just trying to understand the significance of the word field because
Yeah.
it seems like field is like very broad. What's so special about a field? Like why is a field interesting? What is the
Yeah.
connection with
That's what I'm
particles, for
saying.
instance?
It's not. I mean, like a field is as interesting as you think change is interesting. A field is just a
Mhm.
language. A field is just it's kind of funny because it's both a technical term and a non-technical term, right? And the technical definition means something very different from the, but I guess it's kind of fitting because it is like we mean in a very general way. Like if something is changing, like what do you mean by change? Like this part is changing different from this part. Like now you have a field, right?
I
So
think
it's like a wave permeating throughout is how I'm kind
Right.
of
Well, a wave
visualizing.
is even more specific, right? A field doesn't have to take the
Mhm.
form of a wave. It just has to
Mhm.
have the property that like a wave has to be repeating, but a field just has to be changing. So it's like an even more primitive, like
Mhm.
but
I see.
I think you do have to assume though that the change can be continuous. I think it's a very natural thing.
sure. So that's part of the definition of field, that the change is continuous. So okay, yeah. I guess if you think, yeah, but we're not talking about crazy discrete changing phenomenon right now. So.
I think it's a very natural leap of faith. If you assume that's true, then there's got to be something that sort of permeates all of the universe in such a way that the value can change. And then
Yeah, but
that
you don't
leap
even need
of
that assumption. I think you can define a field simply as like parametrically dependent change. Okay, so if your
Yeah.
change you're talking about is not parametrically dependent on anything, okay, then maybe it's not a field. But okay, give me one example of that.
Wait, hold on. I want to make this more concrete because right now it's extremely abstract of what we're talking about. Let's take the example of the temperature field that you just talked about. Let's say I'm in a room and it's, bounded. I'm not looking outside the room, and the temperature varies in different parts, maybe by a little bit, maybe by a lot. Tim, you mentioned that fields are connected to particles. Where's the hell is the particle in this
Wait, no, that's the
example?
second step. Are we good in the field now? So first we have to establish why change means field. And then the second part is we have to establish why field means particle. So are we good in the first part yet?
I think so.
Okay,
Yeah,
then let's
I
move
would say
on.
so.
Let's
Yeah.
move on then.
yeah, yeah.
Yes.
Temperature isn't the best example, but it does work. So
Oh, absolutely. We have temperature particles.
yeah,
Oh,
yeah,
tell me, what is
but they're not
that?
fundamental. Like for example, like then you
I
have to dig
mean,
a little
wait,
deeper.
could you not say phonons are temperature? Because
No,
they are variations in
yeah, yeah,
the.
but hold on. What I'm trying to is to bridge that gap, right? You have a temperature, then you have to try to understand where does temperature come from.
Right.
Then if you assume that there's a medium, like air molecules, let's say, then
Mhm.
the temperature variation will come from some sort of undulation of the air molecules. So like for example, temperature wave in like a temperature particle in air, yeah, will be sound waves, right? These are not like
Mhm.
fundamental particles, they're kind of emergent. Or like temperature particle in this case in a metal is also some type of like phonons, for example. I mean it depends on the medium now. But yeah, so if you say there's a field that's allowed to vary, then it's allowed to undulate, and there is some sort of excitation, propagation of this
It's allowed to
property.
spike. It's allowed to spike then. And when it spikes, we call
Mhm.
it a particle.
Mm. Can you describe like if I let's say have a single electron in the lab, can you translate that into the language of fields, like just to make it really concrete? Like there's just an electron hanging out in a box.
Yeah.
How would I describe that in language of
Yeah,
fields?
no, actually that's easy. Imagine you have a measurement device that just beep
Okay,
beep beep when there's an electron nearby, right?
sure.
So then that device away from the electron, there's no beeping. When you get closer to the electron, it beeps more. So you can think of that reading as a field. And that's literally what an
Mm.
electron field is. It just reads
Wow,
how
that's
many
good.
electrons.
That's
So
good.
it's like that's the electron comes from the electron field.
Wow, that was awesome. I was going to give a way lamer answer.
I okay, it's a slight aside, like a measurement device has to like interact with this field. So if you didn't have the measurement device, would the field exist?
Eh,
Well, in quantum mechanics, interactions are the only things that exist.
Oh, okay, okay.
That's why
All
it's a
right.
very clever explanation for this.
Okay. So let's come back to this. So really interesting points that you mentioned, Tim. I want to touch upon like maybe this relates to it of what the connection is between particle physics and this discovery in terms of the field. Like so you're saying that this cosmological like constant or this rate of expansion of the universe is no longer constant anymore. So because there's change, there's a field. So what does that imply for particle physics?
That means if you imagine there is a dark energy meter, beep 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 beep, right? If there's
Yeah.
large dark energy, it beeps more, then there's a dark energy field, and it means that a dark energy field could vary, right? I mean, in order to solve the tension in the data, minimally it has to vary across time. You know, it has to get weakened, right? I don't know, like
But as you said, because of relativity, that must also mean that
right. It must also mean that maybe it's a little higher here than there. That's a
it has to be.
possibility.
It has to be.
Like, yeah.
Your reference frame, yeah.
Yeah. And that just means that if you look a little closer, then dark energy must be made of this thing. And if associated with this, like so of course the dark energy field now can vary, then it could be emergent, right? But the simplest explanation that people always go first is that maybe it's fundamental. And that means the dark energy field will be associated with these dark energy particles, right? So if you have a meter that beep 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 beeps how much dark energy there is, secretly it must be measuring something, maybe the amount of dark energy particle or some property of this dark energy particle around. So that means that and this is and let me just remind the listener, this is a totally different view on what dark energy is. We used to believe that dark energy might be sort of some property of the universe, like an interest, like an interest rate, right? And now all of a sudden, if that, a constant interest rate, and all of a sudden now this is a property, then basically you have to have this, I don't know, these little. It's almost like these little mini bankers everywhere in the universe.
You need the Fed. Like someone's changing the interest rate. Like who is changing the interest rate? Is there some person that's dialing it?
Yeah, but more than that, that person has to be everywhere in the cosmos, right? So you get these little.
Obviously, we're talking about some
right. so you get and the Fed of the universe becomes these little, I don't know, dark energy particles. Then it has then now, instead of having this constant thing that's just a property of the universe, you have dark energy particles everywhere. And in a way, it's a little comforting because, like, for so long, people think, well, I have no clue what dark energy is. Now there's sort of a candidate. Be like, hey, look, guess what?
Wait, no, I want to push back on that. We thought we knew what dark energy was. We thought it was the vacuum energy, but I mean, obviously there was the ridiculous fine-tuning problem, which we can get into, of course. But at least the behavior of it made sense.
Yeah, so I guess we can debate whether this makes more sense or not. Maybe in some ways.
That is the debate, right? Yeah. Does it make more sense as a constant, or does it make more sense?
Yeah.
Oh, I didn't even realize. I thought it was like. I thought it's showing more conclusive evidence of it not being constant.
Yeah, well, that's what we said last week, and I was a little excited / depressed over that because of how much it flies in the face of things that we already know. But now I don't know. It's not okay. It might not be sobering, but I don't know. I feel like it's splashed a little bit of cold water on my excitement / depression about this whole situation.
Yeah.
Yeah. Yeah, I want to quickly touch upon like this connection between how it's different in space, and also different in time, like how those two concepts are connected to each other. So maybe it might be helpful to describe to the audience, how do you even measure this? Because we call this dark energy, assuming it doesn't interact with light or maybe very minimally interacts with light. So how do people know that it's even happening? And then how do you know that the rate is different? Maybe we can like summarize what we discussed in the past episode.
Yeah, I mean, at its core, they basically try to look at how fast things are moving away from us, and it's as a function of its distance, how far away it is, right? Think about it. If something is really super duper far away, then when the light reaches us, that light has traveled a long time, and that light has experienced more expansion of the universe, basically. Yeah. And then by comparing how far objects are and how much their light has gotten stretched out, they can make a plot. Yeah. And experimentally, for a long time, this plot is roughly sort of like linear. You know, like the further away, the more stretched out the light is, and that's sort of expected. But now, the trend now is is changing just a little bit more. It's not no longer a simple fit. Like at the end of the day, it's just the fit on a plot does not it's not enough to fit a simple line through it anymore. They have to adjust it, and that's why there's an evidence that shows that, hey, look, it's not what we expect.
So okay, so it's a fit to a plot in the sense, and now it's no longer constant in some sense. There's kind of a varying behavior that they've
Yeah,
noticed
yeah,
and are honing in on.
right. Like a good analogy, maybe like if you like the banking analogy, imagine you had 10,000 people, like one person saved $1 10 years ago, and another person saved $1 9 years ago, and another person saved $1 8 years ago. Well, then you look at the bank balance. Well, how much money do they have today? Then you can infer, you know what? There's a constant interest rate, right? And you fit a line through it. But then you might get surprised, be like, hey, this guy invested $1 20 years ago, but hey, look, it doesn't match up. The money he gets doesn't correspond to like a 1% interest. It's like he's getting a little less. Like, what the heck? You're gonna go to the bank and complain, right? I mean, that's pretty much what's going on. Like
Okay.
someone's
I don't
getting
understand anything about finance. So that was actually harder for me to understand than that.
Oh, is that right?
Yeah, once we start
I understood it. I liked it.
I'm just like maybe the first grader way to say it is just that, like, everyone knows. Oh, not everyone, but you can understand that when we look out farther into space, we're looking back into time, and when we're looking closer into space, we're looking more recently back in time for the reason that Tim mentioned, because light takes time to transit. So we're actually seeing a photograph of what things looked like a million years ago, and we're looking a million light years out. And when we make our measurements about how the universe is expanding then versus now, we don't see it being like a constant thing. It seems to be like the expansion behavior is shifting.
Yeah, no, that totally makes sense. I kind of want to touch upon like I know there's no simultaneity that exists in relativity, but here's my question: like, would this apply? Because so far we're doing this from the Earth's reference frame, like Earth is the center, and you're seeing everything moving away from Earth, or I don't know what towards, but away from Earth. But if I like move to another galaxy, would I observe the same thing, or like would it be that patches of space like away from Earth are expanding at different rates, and I would notice like, oh, if it's expanding slowly there, and I instantly transport myself over there, I would notice like, okay, things are actually moving further away because in the Earth location. Yeah, I'm just curious
No,
to get your
that's a
take
really
on
good
that.
point, and I think that hits upon like, so one of the things about this thing I mentioned in the beginning, like, so Einstein's theory predicts that if you have some constant energy density, then all of space will expand uniformly. It'll all be stretching at the same thing at the same time. And one of the consequences of that is that no matter where you are in the universe, you'll observe the same thing. So even if you're here, you'll observe everything moving away from you exponentially fast. And if you're in a different place, you'll see exactly the same thing because all of space is behaving the same way. And that fit not only well with the observations, but it also fit well with the Copernican principle, the idea that we do not occupy a special place in the universe. You could alternatively imagine a theory where the Earth is the center of the universe and everything is just moving away from the Earth, and it just looks to us like some kind of spatial stretching, when in fact it's not space is stretching uniformly. It's that the Earth is really, really special and exactly at the right point that we just happen to see. And we don't like that idea, mainly just because every time we've had that kind of hubris in the past, it's been shown to be wrong and wrong time and time again. So we're sort of like beaten into this idea of like, we don't occupy a special place in the universe. That's not to say there are theories about like, perhaps there are theories that say that perhaps we live in a great void, whereas like there's an enormous amount of mass in a concentric circular sphere, like were the Earth exactly the center, then that would make gravity pull everything apart from our perspective, right? But that sounds like a really stupid idea, doesn't it not? So I don't know. I just think that just sounds stupid.
Yeah. I guess Tim, do you have anything to add to that? Like, we're saying that, oh, it like differs in time, but and then differs in space, but these seem like two independent things, like two sides of the same coin. But could it be that it just like differs, like if I were to freeze time? I don't even know how to even describe this because I know there's no simultaneity in relativity that you can't depends on how fast people are moving relative to each other, relative velocities. But let's just say you could like say everybody's at the same time, for instance, like would you, I don't know, would they observe the same behavior? How do you kind of visualize it is my
Well, I
question.
mean, the thing is, so far we don't have evidence for it, and of course, we can't just go to Andromeda and find out what's going on, and we will never get
Mhm.
that data. What we could do is
Yeah.
look at different directions in our sky and
Mhm.
see if that rate is different. I don't think people have
Mhm.
looked into that, but my guess is,
Well, they definitely have. They've
yeah.
definitely like anisotropy. It's
Oh yeah,
anisotropy.
of course on the CMB, yeah, but overall there doesn't seem to be any statistical anomaly that seems to suggest
Yeah.
that any direction is different from any other, except what Mikey mentioned. We have observed some patches that are unusually void,
Mhm.
but that could still be just due to statistical fluctuation. There are patches.
I
There's
believe
some
they're all known to be within statistical fluctuation,
right,
within
basically, yeah,
acceptable.
yeah.
There's no
Of
voids
course,
that are
yeah.
so big that it makes you think twice.
Yeah, of course you can never guarantee, right? Like maybe this direction seems to have expanded a little less, but that could just be that because there's a lot of gravity stuff in there. So relatively speaking, there's less the influence of dark energy is a little minimized, right? And maybe in some other parts there's more void, right? There's the more dark energy. So but at the end of the day, the measurement is statistical basically.
Hmm.
Got it. I want to touch upon like what is the big deal about like now the cosmological constant or this rate of expansion no longer just being constant? Like, why can't you just plug it into the equations and just, call it a day? Is there any sort of theoretical issues that arise when you no longer assume that
That
this is
there
constant,
is
both
there
like in particle physics and general relativity or astrophysics? Yeah.
There is. So you could literally throw in something that just changes nilly willy. You could do that, but then that might break a lot of things. Like for example, if it doesn't obey Einstein's relativity, it could screw with the universe. Like that violation could be injected in all kinds of places. It could mess up like the way black holes are and all kinds of observational fact. So most people believe that if it varies, it has to obey Einstein's laws. It has to vary
Mm,
in the same way, space and time, right? And as a result, it has to make particles, and those particles has to at least be stable. It cannot engulf. It cannot cause the universe to decay, right? It cannot cause instability in
mm,
the universe. But these are the most basic principle of quantum physics and also gravity, right? Like by introducing this particle, we cannot cause a catastrophic collapse of our universe. And you might think
mm,
that's crazy, but just that constraint mean actually we can know a lot about the properties of that field already. Just imposing
mhm.
a consistency. And that's why it's so powerful, this language.
Hmm. That makes sense. Yeah, I would say okay. So, but you impose constraints on it. Are there any other issues that you want to touch upon before we, move to a different part of this subject?
Yeah, just the fact that like I mentioned before, like the idea that the expansion of the universe might be being caused by a constant, that it doesn't fit perfectly with everything we know, but like more or less it's consistent with everything we know. Um, if you even make the slightest jump to say that it's changing even just a little bit, now you have to introduce a ton of new machinery to explain how is it changing, why is it changing, how is it that it's changing and it hasn't made the universe swallow itself the way Tim described.
Mhm.
Um, and not only does it bring in all this new machinery, but most of that new machinery tends to destroy a lot of the understanding that we had already. And that's not to say that this is impossible, but like in the practice of theoretical physics, over 300 years of theoretical development, and you look for patterns as to what ideas are likely to be right and which ones are likely to be wrong, you wouldn't put your money on it, you know.
Hmm.
Yeah.
I see. I see. Um, yeah, so I want to touch upon like what does so now we've kind of described the issues of what happens when it's changing for theoretically, but practice like I guess I want to dig deeper further into it. So what are the implications of it changing? Let's say you keep the constraint, like it doesn't destroy the universe, it, obeys Einstein's field equations, it plays nicely with all the current frameworks of physics, but it's just that it's changing. So Tim, you mentioned, we spent the first part of the episode talking about a field, and so can we touch upon that? Like, how does that? Yeah, just what does that? What are the implications
Yeah.
of that?
Yeah, that's a great question. So just by writing down something that changes, first of all, doesn't immediately reproduce the effects of cosmological constant.
Oh, by no stretch of the
By no stretch, right? You actually have to work very hard, right? So now you have to ask, I have this particle, this field, how can it mimic the effect of an expanding universe?
And how
one that's
hard do we have to work to make it mimic?
yeah. So intuitively, actually, this is very hard because all particles have energy, and energy has gravity. Like and gravity attracts. So the moment you put more energy into this object, gravity will cause it to the space to collapse a little bit more, like not expand. So it's very odd. So how do we mimic that? To mimic that, you need something that's kind of repulsive. Like I mean, I don't know if it's pun intended or not. And also the model becomes kind of repulsive as well. It's like you have this thing that has enough repulsion in such a way that like it mimics the expansion rate of the universe. I mean, that's kind of a tall order, but like you could make it work, kind of. So these class of models are what people call quintessence. It's a terrible name, actually. I hate that name.
Terrible name for a terrible theory. It's just perfect.
Yeah. So people call it the fifth force or whatever, but it's just this weird field. Somehow it's so repulsive, literally and kind of theoretically, that it mimics the behavior of an expanding universe. It's kind of odd. So you could get it to work, but the details are kind of ugly. You really have to like force it to work, basically.
So is like I just to touch upon this, we don't spend too long on this, but just to make sure I understood what you said. Are you saying that people created these theories called quintessence that has like, because as you put in more energy into a system, it will attract because that has more gravity. Energy is has gravity to it. So you want like a more repulsive force in some sense to push things away. Is that right? Or
that's it, yeah. You need something so repulsive that it overrides the inherent gravitational attraction. Of course, you can also screw with Einstein's equation. You can be like, oh, well, Einstein is wrong, and this field doesn't follow Einstein's equation. But no one wants to do that, okay? But
yeah.
So if you say, well, Einstein probably is still right because there's no evidence that Einstein's field equation is wrong, but I'm going to add this ever-changing field, somehow mimicking the effect of an accelerated expanding universe. How can that work? It like intuitively it needs to be repulsive. It's got to have this like weird repulsive force that modulate kind of.
I'm a little confused by something actually. Like let's say that the expansion of the universe is caused by a constant energy density, like the quantum vacuum energy, mostly. Why can't there just be a small component of it that's causing this small deviation in what we see? Like, why can't it be?
Yeah, I think you might be, but okay. I think it comes down to Occam razor, right? It's like you can so here's a cosmological constant, and then here's a changing version of the cosmological constant. You have a few possibilities. Do you pick one? You could be like, I choose cosmological constant, or do you pick the other one, or you have a mix of both? I think you probably can maybe do away with a mix of both, but
That's
now you have
usually what we
more.
do, right? When we see small effects, we're like, okay, it's mostly what we thought, but it's just this weird little new thing. And so,
Yeah, so I don't know the details, but I think a
admittedly,
lot
that
of
approach doesn't work out well often, but that's usually where we start. Right?
I think most people just take Octum Razor. They say, hey, look, either cosmological constant or the other idea. They don't do it like, oh, maybe it's cosmological constant plus a little bit of X, because that might be a little weird, right? Because it's like, oh, guess what? There are two things that mimic that I don't know. There are two things somehow. They are just Goldilocks when the effects combine to give you kind of this expanding universe picture. A little odd, but
Okay, maybe this is a good time to bring in this discussion of fine tuning, though, right?
yeah.
So, because like, okay, so one of the things I mentioned is that particle physics predicts a constant energy density, and constant energy density predicts this very specific behavior of universal expansion, which we see mostly, but we're starting to see a little bit convincing evidence that it's a little bit different from what we expected. Um, yes, it's true that particle physics predicts this constant energy density, but it predicts way too much of it. So
yes,
it predicts it's constant, but the value that it predicts is really off. So that's one of the biggest problems in particle physics. We call it the cosmological constant problem, and it's if you could solve it, you would be the most famous theoretical physicist of all time, probably even perhaps surpassing Einstein. So it's considered a very big problem in physics why this value is off. But the fact that it's constant, we think is quite certain. And the fact that it's constant predicts this behavior, which we almost observe aside from these, recent experiments, or not actually, I mean, it's been building up over time, but aside from these little inconsistencies that we're talking about here. Um, so from that perspective, you could also argue like, well, we get the value so wrong, so maybe there's all this other stuff there that could be going on that I don't know.
I think
Really aesthetic.
particle physics find comfort to think that, oh, maybe we got really lucky, like this universe won like a lottery
That would
three
be the
trillion.
multiverse. That would be the
Right,
multiverse.
basically, yeah. I think the conventional wisdom is like the universe won lottery 3 trillion times, something like that, in a row to get where we are. So, something ridiculous like that. And but then once you win the lottery, you're good because like it's a cosmological constant. It's not gonna
Yeah.
change, right? So the problem with a change in cosmological constant is that while you won the lottery in when the creation of the universe, and you also won the lottery again later
Oh
on,
yes, you have to win the lottery twice.
you basically have to keep winning the lottery in such a way that the cosmological constant, well, not no longer a constant, or the let's call it the dark energy field. The dark energy field doesn't blow up in your face. You gotta like keep that tamed, right? Basically,
Ah, that is
and that
yeah. Yeah,
and
I
that's
see that. Yeah.
that's a much harder pill to swallow as a particle physicist. You're like,
Not only
nah.
did one constant happen to be right, but the constant happened to be right, and its behavior after that happened to be just right. That's way more of a nightmare.
Yeah.
So that's the fine, is that the fine tuning problem, or is that what you were referring to when you said fine tuning problem?
Oh yeah. So just to go back on that, like I think we can even relate back to something I said earlier, like the Copernican principle, right? Like so,
Hmm.
the first heliocentric models of the solar system assumed that the Earth was at the center and that we are special, and that God loves us and He put us at the middle because the middle is special, and everything in the universe can be explained that way. And that is a kind of a fine tuning, right? Like, so you're assuming that we occupy some very specific place in the universe. And if I'm just a little bit off, then your whole picture just falls apart. And humans have had this idea hundreds of times. I mean, I guess if we're talking about all humans, probably billion, like, an uncountable number of times, because humans have a tendency to be biased into thinking that we are special. But every single time we've theorized that we are special, we've been proven wrong by observations and measurements. And so it's almost more of like a thing that scientists have learned to just stay away from. Like, never assume that we are special. It's almost like a dogma, if you will. It's
Hmm.
possible that that could be wrong. Maybe we are special. And maybe everything is just a giant conspiracy to make things look like a certain way to me. Um, and I don't know, just from a philosophical perspective, such viewpoints have not produced any measurable progress in the past. And so, okay, we'll entertain the idea, but we're not going to take it too seriously. So this is kind of the idea of fine tuning, right? It's like how hard this is, like how hard do you have to work to explain things? Like, are things just natural, quote unquote? And this is a technical term we use now, naturalness. Like if you just drop me off somewhere in the solar system, will I see the same thing? Like, there's no experimental test for this because, as Tim mentioned, we can never go to another star system and see what the universe would be like from there. But just from a philosophical perspective, it feels right and it's paid off. And if you think that you are that special, then I don't like you.
Yeah, but
I see.
but I guess we're forced into this uncomfortable situation. I guess in a sense, like physicists wants to be humble, but like, but then in this situation, what do? It's like when faced with the experimental data, you cook up with these model, but the model is almost very not humble. It postulates that our universe is so special. So physicists are put in a very difficult spot. Either accept the data, and if you trust the data, you will say that, hey, something's going on, but then you'll lead to another very uncomfortable spot. So there's no right answer at this point, basically.
Well, it's an uncomfortable spot, but I think we know what the right idea is because every single time we've been forced to deal with this tension between our hubris and the truth always has beat our hubris, right? So I think
it's true.
There's never been a case. There's no counterexample. I'm metaphysically certain of this. And so
yeah. Although let me add one thing. Like these so-called quintessence model, changing dark energy model, this is what we will call a phenomenological model, right? We're just saying that, oh, if the thing is changing, what is the minimally viable? I mean, it's almost like in the startup world, this is like the minimally viable product. It's the minimally viable model. It's just a whole bunch of whatever random things slapped together to fit the data.
People outside the startup world would not appreciate how pathetic.
Yeah, so basically we slap together a bunch of numbers to fit a line. And there's no explanation whatsoever offered to why the hell there's even a field that is mimicking the effect of a cosmological constant. No explanation whatsoever. It's just that, well, it's just there. What are you gonna do about it? So we don't generally physicists don't like that. You know, it's not, that means that it's not a true theoretical model. We don't have the complete picture, and it's probably true that we don't have the complete picture. But for now,
it's almost like a placeholder. Would you say like these phenomenological models are almost like all physicists deep down inside, even as me and Tim are phenomenologists, even we know deep down that these are just placeholders for where we'll explain later, right?
Indeed. Yeah, placeholder for I don't know how many decades. But yes, for now, placeholders that we don't fully understand, but kind of captures the intuition and essence of the physics.
At least we can put the problem in a box, right?
Basically.
and put a placeholder here, and then we know what to work on. But I mean, that's a big part of I think it's underappreciated. That's like actually 80% of the battle, I would say, right?
Yeah, no, those are all really interesting points. I also wanted to ask you guys to, maybe touch upon like I guess when I first heard about dark energy, I heard that it's like back when, we're all mostly under the impression that it was constant, that's fine-tuned to like 120 decimal places or something
That's what I
really
meant by the value.
ridiculous. Yeah, it's really ridiculous like that. So, I mean, is what they're detecting like 121 decimal places off, or like what is the scale of it like changing, for instance?
Oh, okay. Well, I think Tim should answer that because he's more well read on the topic. But I just wanted to mention that I just want to emphasize the point I made earlier, or reiterate, yes, so the predictions from particle physics predict a constant, some constants. What we observe is some constant, and those constants are off by a ridiculous. It's wrong by a ridiculous amount, but they're both constant, and that is provides so much security. I cannot explain how much security that provides. Me, at least, like in terms of my own like mental anxiety about my understanding of the universe. But if you even say that it changes even a little bit, then the whole house of cards just comes from crumbling down, and yeah.
Yeah, let
So
me
yeah,
just tell
how
you.
much is the thing fluctuating? I don't even know.
Yeah, I don't remember the exact number, but it's no more than 10 to 20% over the age of the universe. So this is changing very slowly, right?
Wait, 10 to 20% sounds a lot. Can you explain to the viewers how that's
I mean, they just fit a line to
because
see
you're
how.
saying since the age of the universe, so that's like a very okay. Well,
Yeah, but I mean, but that's really slow, right? But I
because
don't.
the age of the universe is so low, so that
Right,
yeah.
right. Yeah, but it depends on the oldest. Well, if you want to dig into details, you have to look at the oldest object that they see and the youngest object that they see, where they draw the line, and then how much delta there is. I
Wow,
believe it's
20
not.
30% sounds like a lot, but like I actually can't separate how significant that is given the fact that the universe
Well,
is
don't quote me on that. Don't quote me on that. It might be a few percent, but
sure.
but actually, it's a very slow rate of change, and actually, this is one of the reasons why it's so odd. Because in particle physics, things change so quickly. You're talking about particles, man. Like now, you need like a super procrastinator. I don't know how else to put it. Like there's this.
I was gonna say sloth, like the
Yeah,
slothiest thing you
like
could ever imagine.
the slothiest object in particle physics that changed just like a
By
tiny.
far, by far.
Right, by the tiniest amount over the eons. Like, come on, like we've never seen something like that. So the amount of like it's so ridiculous. It's just so little change, but it's changing. That it has to work. So
It's
it's
also
very
like a very important philosophical point, right? Like, say, so imagine that like you're trying to shoot an arrow from New York and trying to hit something in San Francisco. If you're off by even a trillionth of a trillionth of a trillionth of a degree, by the time you get to San Francisco, you're gonna be off by like, some large amount, right? And so that's why this percentage sounds big, even though it's caused by a very, very tiny change. It's because the age of the universe is so big.
right.
And the slothiness that we're talking about is like really ridiculous if you think about it that way. It's I don't know.
It's almost like imagine you're driving. You have to just gently change how much you step on the gas by the tiniest amount so that it
is
fits
both the
data.
laziest and most precise sloth
Right.
ever
That's
existed.
basically it. So that parameter is so tiny. It's like, but then it's gotta be there. So that's and at the end of the day, this is fine tuning, right? Like, how is it that there's such a precise throttle from this particle physics thing? Because everywhere else, you look at every other particle, the photon, gluon, whatever, no particles has ever had such a tiny throttle. Like, no.
Yeah.
Like,
The sensitivity of this throttle is ridiculous.
yeah. So that's one place of the fine tuning, and there's a bazillion more because now this thing can change however it wants. And there's all kinds of problems. For example, like, since it's a particle, can it decay? It has to just not decay. And also, since it's a particle, it also has quantum mechanical effects. How can it not be destroyed by quantum mechanical effects? We talked about in previous episode these what we call these loop correction. Nobody can answer that. But anyway, like, so many things have to come together, just cancel each other out in a way that it put the gentlest, slothiest throttle in the interest rate of the universe to make it work. Like that's what it might imply. So I don't know if that's comforting or not.
I don't know if this is a good analogy, but it's kind of reminding me of this scenario where, like, let's say you have like a bunch of friends in a room, right? Okay, if you want to bring in a table, you can bring in a table. That's a constant. We know it's not going to ruin the dynamic of, like, the social dynamic. But if you bring in another person, then is this person a murderer? Is this person like, like what is this person's sleeping habits? What are the likes? And just like you have to ask a whole lot more questions. And what we're seeing now is that maybe the universe has introduced a new person into this room, but they are the most boring, dullest, lowest moving person that anyone has ever seen in recorded history. And that seems to be like the only thing that would explain it. So
Right.
It's a little bit of a head scratcher.
but yet it plays a very special role, right? Like no other particle dictates the structure of the universe as much as this particle.
Yeah.
But yet this dark energy particle, its only job is to govern the expansion rate of the universe. That seems like such a contrived purpose. Like
it does, yeah.
Seriously.
But who knows? Maybe it just seems contrived because we're so stupid. Like,
That's also true. That's also could be true. But we don't know.
I wanted to ask you guys, like, so Mikey, when you're talking about dark energy, at least when it was constant, mentioned like, oh, it expands space, and because there's more space, there's more of, quantum fluctuations or dark energy, and that creates, so essentially creates more of itself.
Yeah.
And so I'm wondering, like, from that perspective, and also from the perspective of changing, clearly space and time, as we've talked about in many episodes, is most likely, a field, and also not fundamental potentially, which we've touched on in previous episodes.
Yeah.
And so how does this field interact with, like, I guess, like the gravitational field? Because Tim, as you're saying, gravity is king. So does it, like, I don't know, does it create more, like, more gravity as well? Or like what? Yeah, how do I think about this?
Yeah, so the interplay is complicated, right? So basically there's a strong repulsion, and then the repulsion depends on the distance. So you have this this quintessence field, whatever you call it. People call it quintessence field. It was there's some repulsion, and as the universe is expanding, it gets diluted. But somehow the profile of their repulsion, which depends on distance, sort of adjusts itself in a way that as you expand, you also repulse just enough so that it kind of mimics this exponential behavior. By no means is guaranteed, but it mimics it. So unlike the vacuum energy, you have more space, you have more vacuum energy, it just scales up. Here, when you move the particles, the quintessence, let's say particle, a little further apart, I mean, these are really particle waves, right? The waves are a little more apart. Their repulsion profile adjusts so that the repulsion keeps it up, right? Of course, at some point you go far enough. So basically, there's something what we call very flat potential. So their repulsive force doesn't depend too much on their distance. But when they're far enough away, the repulsion does go down a little bit. So that's why the slowdown of the expansion of the universe. But that's how they mimic it. So it's pretty awkward.
Yeah, I guess can you give like an analogy? Like, I mean, even if it's like really an absurd analogy, like I guess Mikey, the friends in a room, or Tim, like I don't know, like some like, with interest rates or something, like just to help me wrap my arms around this.
Yeah, I don't know. Can you say that if there's an extra person in the room that nobody likes? Well, it doesn't. I guess it doesn't interact with everybody. It interacts with space and time. Like imagine nobody can see this friend. Okay. But this friend knows about. Okay, well, imagine everybody. Okay, how about this? This is a really weird analogy, but imagine you have a bunch of friends. Every friend has a bodyguard. The bodyguard is like space and time, okay? But the bodyguard really doesn't like this extra dude, okay? Right? It comes in, it's like, and the bodyguard just like, oh man, stay away from this person. We don't like him. Like the bodyguard just tell everyone to walk away. I don't know. Then it's like expanding. Kind of. I don't know.
I mean, but then there's like, if the bodyguards are like space and time, then there's more bodyguards that appear as you go further away.
The analogy doesn't cross over into that.
Yeah, well, this is assuming we don't have cosmological constant. We just so more space doesn't make more space, Then it's just that the bodyguards doesn't like the quintessence, so they expand away, kind of. I don't know.
Yeah, but this is like space time itself expanding,
right? But it's caused by the quintessence field. It's caused by the repulsive energy of the quintessence field, which follows Einstein's equation, will cause the space and time to back react.
So,
but, yeah.
is it is it kind of like I mean, could an analogy be like if I okay, this analogy doesn't hold in many fronts, but let's just say like you had like particles that were like attracted to each other, and then you put like a single particle in the middle that's just kind of repulsive to all the other particles, and they just sort of like go away
Right,
from
yeah,
that.
but that's
Is
not
that
a good analogy because the quintessence field cannot directly interact with all the other particles. Because that causes
Mhm.
tremendous problem. Because otherwise, if it interacts with other particles, like moving my hand, I'll make quintessence particle. The sun would
Mhm.
lose energy to quintessence particle, and the sun will stop shining. And that would not fly. Like this quintessence, its only job is to talk to gravity and to almost relay that message, be like, "Hey, go away." Um, but the gravity itself is not doing it. That's I mean, at the end of the day, it is just you got to follow Einstein's equation, and it's yeah, there's bound to be some level of abstraction because it's the geometry of the space time itself reacting to the quintessence field. So yeah, I'm not sure how best to put it.
Yeah, I'm kind of wondering about the I had another question in my mind, but now it's kind of it's escaped me. Um yeah, I don't remember what it was. I guess like just the notion of like space itself expanding at different rates. And no, now I remember the question. The question was like, would I mean, does it indirectly interact with light? Because we're clearly observing this through how light is impacted by the expansion of space and time. So is there an interaction with light, or how do I think about that?
It
No, it
cannot.
absolutely cannot be. Well, okay. We did talk a little bit about how it could be connected to the dark sector, and if we believe the dark sector is connected to light, then that could. But the simple. Okay, sorry, I don't even know why I said that. The answer is no. Yeah,
It
like
has
I
it
mean,
has to be
interacting with
dark.
light in the sense that like the objects that interact with gravity also interact with light. So
Mhm.
we see these gravitational effects and we observe them through light. So I guess it does, you could say it does interact with light in a sort of composite way by talking to someone that talks to light, but then
Mhm.
everything talks to light.
Yeah. So there cannot be direct interactions. Yeah, it has to be through gravity because if this quintessence particle can talk to light, it means they will decay.
It means we
It
could
mean
see it directly.
right. That means dark
We
energy
wouldn't have to
become
infer its existence from its effect on other things. Yeah.
dark energy wouldn't be dark energy anymore. But
Yeah,
actually,
it wouldn't be
actually,
dark.
but actually, Mikey, I maybe this plausibility could be viable in some way. I mean, this is now in the research frontier, right? Like maybe this quintessence thing could decay into light. Then dark energy wouldn't be totally dark anymore. If the
Yeah,
decay rate is low enough, right? Then that
sure.
means there's a really, really faint glow of the universe everywhere because quintessence is decaying. And
Uh-huh.
maybe in some weird way this could explain the weakening of the quintessence. But
Uh-huh.
my immediate reaction is probably not, because
Yeah.
what are the chances that you make a model that works? But you have to work out on a blackboard. There's no other
Yeah.
way. This is
Yeah.
research level question now. Yeah.
We are at that point.
Yeah. So I realize we're almost at time, and so wanted to give you guys a chance to leave the audience in our tradition with any words of wisdom that these experiments and dark energy have taught you.
I guess for me, like through the whole evolution of this story, right? It started with looking at some Google News headlines and then ignoring them, and then talking to Tim, and then being like, oh, like maybe this is something real and really serious. And then talking to Tim again a week later and being like, I don't think this is, I don't think this is so good anymore. And I just think that that's like it's been a while since I've had that back and forth. It's been a while since a topic in fundamental physics has kind of created such a potential for this kind of back and forth. And so, but that's really how science works. And if you look at the history of all discoveries, it always goes this way. And so, um, don't run from it, embrace it.
Yeah, I would say the same thing, right? This is what particle physicists live for, or astro particle physicists. Yeah, it's almost like what is it? Isn't like when you lose something, you go through 5 phases of like grief or something. This is kind of it's kind of similar. When you see new evidence, there's like 5 phases of whatever it is. It's like there's intrigue, there's disgust, and there's
Yeah.
anger.
Yes.
Because because when there's new physics, almost there's no good option. That's basically because probably, however we slice this, we're not getting it right. But the hope is just that maybe we can capture a small nugget of truth. I mean, that's what it's really about. Maybe all this crazy discussion, even 5%, 1% of it is correct. I mean, that's what physicists chase after, right? But I sure hope that, I don't like this quintessence idea, but maybe, just maybe, 1% of it captures some essence of how our universe works, and that's
And if
better
it
than.
does, yeah.
Oh man, if it does, it's
If
big.
it does, if even 1% of it does its job, then it will. If even 1% of it works, then it will have done its job.
Kind of. Yeah.
Fair. Yeah. So on that note, I want to thank Ari for joining us, and we'll see you all next week.
All right.
Thank you all.
Bye.
Bye.